Here are the primes, laid out on a line. 2, 3, 5, 7, 11, 13. Down at the start they crowd together, almost elbow to elbow. But watch what happens as you walk to the right. The dots begin to thin. The empty stretches between them get longer. Between one prime and the next there is a gap, a run of numbers with nothing prime inside it. Near the beginning those gaps are tiny, just 1 or 2 steps. But by the time you reach 113, the next prime is all the way out at 127. That is 13 numbers in a row without a single prime among them. So here is the question that runs underneath this whole video. How big can one of these gaps get? Is there some ceiling, some longest possible run of prime-free numbers that the primes will never let you exceed? Or can the empty stretches grow without any limit at all? The answer turns out to be strange, and you can hold both halves of it in your hand at once. Let us just measure the gaps as we go and keep a record book. Every time we find a gap longer than anything we have seen before, we write it down along with the prime it starts from. The first real gap of 4 opens up right after 7. A gap of 6 shows up after 23. After 89 we get our first stretch of 8 prime-free numbers. Then a jump to 14 after 113, 18 after 523, 20 after 887. And then something that feels almost sudden. Just after 1327, the primes go quiet for 34 numbers in a row. That is the first gap that really surprises you. Everything before it grew slowly, step by step, and then this one nearly doubles the record in a single jump. Keep scanning and the records keep falling. 36, 44, 52, 72. The empty stretches just keep setting new highs. There is no sign of them settling down. Now instead of hunting for gaps, let us build one. Pick any length you want, and I will hand you a run of that many consecutive numbers with no primes inside, on demand. Say you want a desert of length 4 numbers in a row or composite. Here is the recipe. Take 5 factorial, which means 5 times 4 times 3 times 2 times 1. That equals 120. Now write down the 4 numbers 122, 123, 124, 125. Every one of those 4 is composite, and you can see exactly why. 122 is even, 123 is 3 times 41, 124 is 4 times 31, 125 is 5 times 25. 4 numbers in a row, not a prime among them, and we built it deliberately. The same trick gives a desert of length 5 from 6 factorial, or length 6 from 7 factorial. Whatever length you name, there is a starting point waiting. The reason this always works is one line, and once you see it, you will never forget it. Take the length you want, call it L. Look at the factorial of L plus 1. That factorial is the product of every whole number from 2 up to L plus 1. So every one of those numbers divides it evenly. Now add 2 to the factorial, then 3, then 4, all the way up to L plus 1. That is your run of numbers. Take any one of them, the factorial plus some number k. The factorial is divisible by k because k was one of the things multiplied in, and k is obviously divisible by k, so their sum is divisible by k as well. Every number in the run has a divisor sitting right there in plain sight, which means every number in the run is composite. That is the whole proof. So if you want a desert of 1,000,000 numbers, you take 1,000,001 factorial and add 2, 3, 4 on up to 1,000,001. 1,000,000 consecutive composites, guaranteed, no searching required. There is a catch, and it is a funny one. This construction proves that deserts of every length exist, but it drops them absurdly far out on the number line. Think about that 1,000,000 number desert we just built. It starts at 1,000,001 factorial. That number is not big in any ordinary sense. Written out in full, it has more than 5 million digits. You could not fit it on this screen, or in this whole video, or in a stack of books. The construction is honest, but it is wildly wasteful. Because here is the thing, the real gaps show up much, much earlier. Remember that surprising gap of 34? It happens right after 1327, a number with 4 digits. The factorial recipe asked for a desert that long would place it out past a number with dozens of digits. So the construction is a proof, not a map. It shows you that long deserts must exist, but the actual ones are hiding far closer to home than it would ever suggest. If you step back from the records and just ask about a typical gap, there is a clean answer, and it comes from the deepest result about how primes are spread out. The primes thin out at a very definite rate. Around a number x, the average gap between consecutive primes is close to the natural logarithm of x. Near 1,000, the average gap is about 7. Near 1,000,000, it is about 14. Near 1,000,000,000, about 21. So the deserts, on average, keep getting longer the further out you go. And I checked this against real primes, not just the formula. In a window of 40,000 numbers sitting right around 1,000,000, the actual average gap came out to 13.8, almost exactly the logarithm of 1,000,000. The formula and the real primes agree. This is the slow, steady side of the story. The average gap grows without bound, but it grows gently, like the logarithm. One extra step every time you multiply the size of your numbers by e. Now for the twist, and this is the part worth carrying home. The gaps have no ceiling. We have proven that deserts of any length exist. And yet, infinitely often, the gaps stay small. Both things are true at the same time. Here is what that means. You can find prime-free stretches as long as you like. 1,000, 1,000,000, any number at all. But no matter how far out you go, primes keep coming back close together too. In 2013, a mathematician named Yitung Zheng proved that infinitely many pairs of primes sit within 70 million of each other. That was the first fixed bound anyone had ever found. Within months, the number came crashing down. James Maynard sharpened the method to 600. A large collaboration ground it further, all the way to 246. So it is now a proven fact that infinitely often, two primes come within 246 of each other. No ceiling on how big a gap can get, but a proven flaw that the primes return to again and again. The deserts and the crowds coexist forever. So the empty stretches grow without limit. But how fast does the biggest possible gap grow? That question is still open, and the best guess is beautiful. The average gap near P is the logarithm of P. But the biggest gaps, the record-setting deserts, run larger than average. In the 1930s, Harold Kramer conjectured that the largest gap you will find near a prime P is about the logarithm of P squared. Not the logarithm, but its square. And the real records fit this shape surprisingly well. Near 1,327, the logarithm squared is about 52, and the actual record gap there was 34, the same ballpark. Near 31,000, the guess is around 107, but this is only a conjecture. Nobody has proven how fast the maximal gaps truly grow. We know the deserts get longer forever, and we can build one of any size on command. Yet the exact law for the largest of them remains one of the open questions about the primes. So here is the whole shape of it. The primes never stop. Euclid proved that more than 2,000 years ago, and nothing has changed it. And yet they fall silent for stretches as long as you please. You can order a desert of any length, 100, 1,000, 1,000,000 consecutive numbers with no primes inside, and the recipe fits on one line. Take the factorial of 1 more than the length, and add 2, 3, 4 on up. Every term has a small divisor hidden in it, so every term is composite. That is the tension worth keeping. The primes are infinite, guaranteed to go on forever, and at the very same time they leave silences of every length behind them. No ceiling on the deserts, a floor of 246 that they keep returning to, and a construction so simple you could hand someone a 1,000,000 number gap on the back of a napkin. The primes never end, but they leave room, as much room as you could ever ask for. This was one more in a series on the questions the primes refuse to settle quietly. Stay for the rest.